Welcome to this explainer. Okay, today we are unpacking something absolutely fascinating. You know, whenever we drive through a massive mountain tunnel or stare up at a towering bridge, we really only see the finished product. We marvel at the concrete and the steel, but what we don't see is the incredible, invisible, and frankly microscopic work that goes into these massive infrastructure projects long before a single shovel even hits the dirt. Today, we're going to explore the hidden anatomy of a safe tunnel project.
Section 1. Avoiding massive infrastructure disasters.
Okay, let's dive into this. Human history is literally full of poorly planned ideas that led to absolute chaos. Viral history gives us some pretty stark examples of what happens when humans fail to account for environmental variables. Take the infamous 1986 Ohio balloon disaster, where hundreds of thousands of balloons were released into the sky, resulting in massive, unintended environmental and logistical chaos. Or consider the wildly miscalculated Pepsi contest that ultimately turned fatal just because of a massive flaw in its underlying design. These aren't just quirky historical footnotes, right? They are stark reminders of exactly what happens when ambitious human projects collide with unaccounted-for reality.
So, what does this all mean for us today? When we're attempting something infinitely more complex than a balloon release, like, say, boring a massive hole through a solid mountain, how do we prevent these projects from becoming the next historical disaster? How do we make sure they actually stand the test of time? Well, the answer lies in meticulous, on-site scientific investigation.
Here's our investigative agenda for today. We're going to walk through 4 rigorous steps: analyzing rock and soil strength, managing water and flood risks, monitoring air quality and noise, and finally, mapping the valley's future. Let's get right into it.
Step 1. Analyzing rock and soil strength.
Now, what's really interesting about this is the sheer verticality of the work environment. You can't just drill into a mountain hoping for the best. You have to know exactly what it's made of. You've got geologists actively studying exposed rock layers on an incredibly steep mountain face. They aren't in a comfy lab somewhere. They are out there, literally clinging to the side of a cliff, reading the history of the Earth to understand exactly how the rock is going to behave when we try to build a tunnel through it. If you are an expert out there crouching near an exposed rock face, picking up a rock core sample, looking at it and speaking to the camera, you'd probably say with a lot of enthusiasm, "I'm the project geologist. I analyze rock layers, soil strength, and drill core samples to make sure the mountain is structurally safe to tunnel through." And honestly, that job is absolutely crucial. They have to find the weak points before the heavy machinery ever arrives. This brilliantly illustrates the exact stakes we're dealing with. On one hand, you have geologists carefully measuring a perfectly square soil test pit, gathering super precise data on the soil composition. On the other hand, a massive, uncontrolled, and highly dangerous hillside landslide. Taking the time to measure that test pit on the left is exactly how we prevent the catastrophic, deadly washouts you see on the right. It is controlled science preventing uncontrolled disaster.
Let's move to step 2 and see how this builds. Managing water and flood risks.
Once we understand the solid Earth, we have to grapple with the unpredictable flow of water. Water is pretty much the ultimate enemy of underground construction. Out in the field, hydrologists take incredibly careful water flow readings right at a natural mountain spring. Notice the calm, precise data collection happening out there. If you don't know exactly where the water is flowing naturally, there's zero chance you can predict where it'll slow once you open up a massive tunnel.
Taking those water flow readings near a mountain stream and turning toward the camera to explain the water measurement process, an expert would tell you, "I'm the hydrologist. I measure stream discharge and rainfall data to design proper drainage systems and protect the tunnel from flooding." Analyzing that water movement is absolutely essential to keeping the future infrastructure from quite literally washing away. To put that into perspective and show you just how granular this gets, look at these specific on-site numbers pulled directly from a hydrologist's clipboard. They're tracking a flow rate of exactly 0.78 liters per minute, a water temperature of 12.4 degrees Celsius, and a pH level of 7.1. This just emphasizes how detailed the scientific data collection must be. A slight change in pH could indicate a totally different water source, and a change in flow rate alters the entire drainage engineering plan. It's wild.
Step 3. Monitoring air quality and noise.
Building a tunnel is also about how this massive engineering project interacts with the surrounding environment. An environmental engineer checks an ambient dust tracker right outside the tunnel portal. But if you look at the background, you'll see beautifully terraced agricultural villages stretching up the hillsides.
Measuring dust at the tunnel entrance isn't just an arbitrary data collection exercise, it's an active measure to protect those adjacent communities, their crops and their lungs, from the massive amounts of dust a project like this can kick up.
So the crucial point is really captured by tracking noise. An engineer holds a decibel meter recording exactly 62.3 decibels right next to local village homes, with the tunnel entrance visible just down the road. Tracking these noise levels directly next to the village ensures the project actually respects the daily lives of the local residents. Because let's face it, we can't build the future by destroying the peace of the present.
Let's quickly break down these exact environmental metrics to show the tangible safety boundaries these engineers are working within. They are tracking fine particulate matter, PM2.5, at 42.6, and larger particulate matter, PM10, at 76.3. And as we saw, noise levels are monitored strictly around 62.3 decibels. These aren't just polite suggestions. They are rigorous safety boundaries that literally dictate when and how the heavy machinery is even allowed to operate.
Finally, Step 4. Mapping the valley's future. We've looked at all the microscopic details, but now let's zoom out to the massive scale of the overall challenge. Surveyors stand on a high mountain ridge, consulting their maps, looking out over a vast, majestic, river-carved valley dotted with homes and terraced farms. All the invisible, microscopic work we just learned about, the rock cores, the pH balances, the decibel readings, it all culminates right here. It all exists to protect this sweeping landscape and its people, while simultaneously moving society forward with brand new infrastructure.
Which leaves us with a pretty provocative final thought to ponder. As you look at the sheer scale of the environment compared to the humans trying to alter it, you have to ask, when humans build, can we truly master nature, or do we simply learn how to safely navigate its boundaries? The meticulous data collection we've explored today suggests it's for sure the latter. We don't master the mountain, we study it, we respect it, and if we're smart, we figure out how to safely coexist with its immense power. Thank you so much for joining me for this explainer, and I really hope you never look at a tunnel the same way again.